Hey there everybody. This video is made in my class to help my kids understand this kind of hard topic about algebraic functions in geometry, okay, and how we can take a graph or something and then manipulate it somehow through revolution or through revolving, spinning. You get a geometric shape, right? You get circles and we get cones and we get cylinders and we get other non-easy to calculate shapes. So let's read what's going on here in our first example. So these are notes from class. Hopefully this will help you understand a little bit about algebraic functions and how we do with them in the geometry class. So we have a portion of a vertical line. Okay, so it's important to remember what we're talking about. We have some part of a vertical line, and this is the point that it goes through. And now we get some more information. It's between the x-axis and some graph. Okay, so let's just look at what that is, right? So we have a vertical line, right? And it goes through some point x comma 0, which means that's on the y-axis, rather the x-axis, because you wouldn't have a y value of 0 anywhere else. Okay, so this is the x-axis. Right, and here's the y-axis somewhere over here, which we don't know about, right? We don't know anything about the y-axis. We don't know how far this point is from the y-axis. We just know that there's some vertical line. Okay, so part of this vertical line that's between the x-axis and this graph of y equals root x. Okay, so if you know your algebra, y equals root x is an ever-increasing function with a domain of positive x values and a range of positive x values. Okay, like some points, if x is 0, right, the square root of 0 is 0. If x is 1, the square root of 1 is 1, right? So these are some points we can plot if you don't know exactly what's going on. If x is 4, the square root of 4 is 2. Right, but I really don't like doing this with these kind of problems because this x comma 0, this is not a specific point, right? This is some random point, that a not countable point, right? We want to get it out of the concrete and get it into some abstract. So this is the portion of the line that we're talking about between the x-axis and this graph. Okay, and we're going to revolve this around the x-axis. So we're going to have some type of a shape, of course, and when we revolve something around a central axis, we get a circle. So this is going to be a perspective circle, right? So we're drawing it as an oval because that's what a circle looks like if you turn it from its side. And since we're looking at it from the side-ish, right, you got to kind of use your imagination, where this circular area here is the base of this shape. Okay, so we have a circle, and we're going to call this the disk. A round object that is rotated by a central line is called a disk. So that's what we're going to use as the terminology in our problem. So this is what's going on. This says sketch the problem situation. Well, I have just sketched the situation. It's this vertical portion of the line that's being revolved around a central axis. Okay, what we're going to get here is this becomes the radius of your circle. Okay, so a couple of these things. Express the area of the, give the coordinates. Sorry, I got to give some coordinates. We know that the origin is, of course, 0, 0. We know that this random point here is called x comma 0. So what about this point up here? Well, because it lies in the vertical path, right, the same here, it has an x coordinate of x, right? That's the same x coordinate as what we had below. But then we have a y coordinate, and it says we have to express it in terms of x. Okay, so we know over here that y is found, any y value is found by taking the square root of x. So that's this equation that we were given in a problem. So every y value is found by taking the square root of whatever x we have. Okay, and this is a pretty hard concept for kids to understand. The x value, of course, we've had x coordinates in forever. But now the y coordinate is no longer called y, because we're figuring out how do we calculate that y value. Well, in this problem, we calculate every y value along this yellow line by doing the square root of the x value. So the y value is the square root of whatever x value we pick, right? Which is why it's nothing specific. So if our x value was 25, then your corresponding y value, the square root of 25, would be 5. But we don't know a specific x value yet for our problem, which is why we leave it written like that, right? A more confusing, complicated kind of way. So there's your coordinates. Express the area of the resulting disk. Okay, so we know that the area is a circle. So the area is the formula for a circle, which is pi radius squared. Now coming back over here, remember it says as a function of x, which means I don't want to have a r in my equation, right? R would be radius, so I want to have it as a function of x. So as we discussed earlier, the radius of our circle is found by doing the y value, right? This is a vertical distance, and in geometry, a vertical distance would be represented by an algebraic y value. So we're going to take the y value of our point, which is the square root of x. Okay, so this is your radius. The radius is found by the y value of your coordinate, and the y value is found by taking the square root of whatever x we have, right? That's what it says up here. The y is equal to the square root of x. Okay, so right, these are algebraic functions, right? This is an algebraic concept. So now we have to do some simplifying. And when I simplify this, squaring a square root, hopefully you know your algebra, and then whenever we square a square root, right, those are inverse operations. So the square and the root go away, and our area for the disk is simply pi times whatever x value we happen to choose. Okay, and the next one says, what if I choose an x value of 16? What's the area of that disk? Well, that area is just pi times 16, and since it's area, the units are squared. Okay, so that's the gist of what we're doing here, right? We're taking this algebraic concept of root x, we are rotating it around the x-axis, which is also algebraic, and that rotation gives us a geometric shape. Okay, in this case, we have a circle that we're going to find the area for. Okay, we're going to simplify the formula and find the area. So let's see if we can do this again for our next problem here. Okay, so here I have triangle cat, and so we know it's isosceles. It's an isosceles triangle with vertex A at the origin. So A is at the origin, and vertices C and T are in specific quadrants on the parabola. So here's your algebraic portion, right? We have this parabola called 16 minus x squared. So if you remember your algebra 1, and I know that you don't, but we should remember your algebra 1, okay, the graph of 16 minus x squared is a parabola. So it's a U-shaped graph that goes down, right? It's a negative, it's a minus x squared. So the graph opens down, and it has a maximum y value of 16, right? So if I plugged in 0, 16 minus 0 squared, I would get 16. Okay, and then as I plugged in 1 and 2 and 3 and 4, I would get a graph that looks something like this, right? This is a classic parabola. It's even, well, that's not very even. It is symmetric around your central axis there, which is in this case the y-axis. So there's the graph of 16 minus x squared. So my problem says that point C is somewhere on your parabola, and point T is on this side of the parabola, right? This is quadrant 1, the positive quadrant. This is quadrant 2, the negative x, positive y quadrant. And A is down here at the origin. Okay, so understanding how to graph this, right? That's the first hard thing, is do you remember your algebra, how to graph this equation? And what are all these quadrant business? That's some pretty difficult stuff. And in order for this to be a isosceles triangle, right, this length from C to A has to be the length from C to T. These two must be equal, which is good for us because that means that your points C and T have to be directly across from each other, right? T can't be way up here or way down here, because then your triangle would not be isosceles, where A is your vertex. Right, the vertex angle is where the two legs of your isosceles triangle come together, and these T and C are called base angles. So there's a picture, right? Understanding what it is to be drawn is the first thing. The next thing says, what are the coordinates, right? What are the coordinates of your points in terms of x? So once again, we have, let's do t. So t is some units to the right, and right is a positive x. So the points of t are positive x comma y. Right? Usually we would do x comma y and we'd be happy. But this says in terms of x, so I can't have y in my equation. I have to have something in terms of x. So let's go looking. What does y equal? What can I replace y with? Well, in our equation, we're told that y equals 16 minus x squared. That's how we find any one of these y values on your graph, is by doing 16 minus whatever x you pick. Okay, so we're going to put that in here. This is your y value, 16 minus x squared. That's how we calculate any one of our y values. So we're going to put that in here, right? So now we have x as your x coordinate, and then we have an equation that involves x in order to calculate every y term. Okay, so that's what it means to have it in terms of x. Now what about c? C is on the left side, and it's equal, right? This is equal distance, so it remains isosceles. So we go a negative x. So the coordinates of C are negative x because they're on the left side of the y-axis. But the y value is the same. We calculate the y value by doing 16 minus whichever x you pick. Okay, and it's going to be the same x because we want this to be an isosceles triangle, which means our lengths have to be equal when we have isosceles triangles. That's an important aspect. Okay, what else? We want the area of this triangle, okay, as a function of x. So here we have our triangle, and we're going to calculate the area. Now, because it's just an isosceles triangle, there is no fancy formula. So we're going to do 1/2 of base times height. Right, just 1/2 of base times height. So let's come over here and look at some measurements. What is the base of this triangle? Hopefully you know the base is across from your vertex. We're just going to call it this one. Okay, this is going to become the base of our triangle. So from the left point T to the right point C, switch up, that is the base. So how far is it from C to T? Well, we know that from the middle to T is x units. And we also know from the middle to C, because it's a distance, is also a positive unit. Whether we go left or right, distance is always positive. So from C to T, that is a grand length of 2x. Right, so your base of your triangle is 2 times whatever x value that you want to pick. Now the height has to be perpendicular to the base, so basically the height is the y-axis here. It runs along the y-axis. Okay, and as it's along the y-axis, it's a y value. The height of your triangle is a y value because any vertical distance that you go on a graph is a y value. And we found the y value by doing 16 minus x squared. Once again, we can't have y in your equation because it says as a function of x. So we're going to replace y with its equation, and the equation of course has x in it, and we still have this 1/2. So let's get to some simplifying now. I'm going to multiply my two numbers together right here, two numbers, 16, or rather 1/2 times 2. 1/2 times 2 is 1, so that essentially cancels out, and now I can distribute my x into both of these terms. So the area of my triangle is 16x minus x cubed. Okay, so that's the area that that's the formula that I'm gonna use to calculate the area of this triangle right here based upon any value of x. Okay, any value of x. So it says find the area when x equals 3, so I'm going to replace through 6x. I'm going to replace x with 3, so we put a 3 there, and then 3 cubed. 16 times 3 is 48. minus 27. So right now, this triangle would have an area of 21 square units. When x is 3, your triangle has 21 square units of area, right? Which is pretty nice. So we have any x values you want to have, we can calculate the area of that triangle. All right, so hopefully you're kind of seeing what's going on here with these right? The triangle is the geometry, and we get the values from an algebra, right? From an equation, from a function that relates some value of x to a corresponding y value with an equation. And rather than writing y, we're going to write down the corresponding equation in each of these cases. Okay, so let's move on to this last one. The region bounded by the x-axis, the line y equals 1/3 of x, and a vertical line going through this point again is does it say what it is? Oh, it's missing it. Is revolved around the x-axis. So we're going to rotate this shape. Okay, so let's see what this shape looks like. We have the x-axis, so let's draw our y and our x-axis. There we go. Okay, there's your axes. We have the line y, so the x-axis is here. Y equals 1/3 of x. Okay, so that's a linear equation with a y-intercept at the origin, and we go up 1 and 3 rights to plot the points. Right, we're using the slope to plot points. The slope is 1 up and 3 over. That's what a positive 1/3 slope does, goes 1 unit up and 3 units to the right. And then we have this point called x comma 0 somewhere. And there's a vertical line that goes through x comma 0. And it, of course, intersects your 1/3 x at some random point. Okay, and it says give the coordinates of the points on the graph. Well, we have the origin, right? That's pretty easy, still 0, 0. We have this x coordinate, x comma 0, on the x-axis, and now we have this purple point. So the purple point is some x value, right? Because it's above the lower point. So those have the same x value because it's a vertical line, and all x values on the vertical line are the same. Now this is, of course, the y value. Okay, and the y value from our equation is given to you by multiplying x by 1/3. So we have the coordinate x comma 1/3 of x. Every y value along that line is 1/3 of the corresponding x value. Rather than x comma y, we write x comma 1/3 of x. And we're going to revolve this around the x-axis. Okay, so anytime we revolve, we get a circular shape. Okay, so there's your circular shape. This is going to become the base of our cone, is what it says. The base of your cone. So we can draw in the bottom side of our cone like this. And I'm going to stop right there just so it looks like a cone. Okay, let C be the cone formed by rotate. Here we go. Here's rotating the area of the triangle. Okay, so we were rotating, let's see, rotating this area, our triangular area, around the x-axis. And when we rotate an area, we get a volume, right? It'll be fun when you get to calculus and get to do that kind of stuff. Around the x-axis. Express the volume of C in terms of x. Okay. So volume is 1/3 of the area of the base, and our base is a circle. So 1/3 pi r squared times the height of your cone. Right, so this is a volume formula for a cone. And let's see what we have. Remember the radius, okay? The radius of our cone was the y value of your coordinate. Okay, so once again, the y value of your coordinate was 1/3 of x. So in place of r, the radius, I'm going to put 1/3 of x, right? Because the radius is the vertical distance in this case. The vertical is always a y value. And then height. The height in this case is an x value, right? From the base, the center of your cone, all the way up to the vertex of your cone. That's an x value. It's a horizontal distance. Horizontal distances are always x's. So we have this equation, 1/3 pi times 1/3 of x squared times x. Now I'm going to simplify. So our algebra says the first thing we do is exponent, so I'm going to square all of these terms. 1/3 x times 1/3 x. And I get 1 squared is 1, 3 squared is 9, x squared is x squared. Right, it's pretty redundant. And then I'm multiplying this by x again. So my final step is to simplify as much as possible. So I have a denominator of 3 and a denominator of 9. So I'm going to multiply those together in the denominator. And I get 27 as my denominator. Now in the numerator, I have pi, I have a 1, I have a 1, I have x squared, and I have x. Now all these are numerators because they're not denominators. They are not on the bottom of a fraction, which means they have to be a numerator. So I get x times x, pi x cubed over 27 as my formula to generate the volume for any random x you want to pick. The next problem says, well, I'm picking x as 12. So that's pi times 12 cubed over 27. Okay, and I don't have a calculator, so hang on, pause. Okay, so I got a calculator and I put this in and I got a final answer of 64 pi, sorry, in cubic units because it's a volume. And there's the bell, which means class is over. So I hope this is a little bit better for your understanding of how we do algebraic functions in geometry. Sorry, okay, I'm gonna get a drink of water. Goodbye, guys.